Welcome everyone to a series of lectures where we're going to be discussing regularization. Regularization in general seeks to solve a few common model issues by minimizing model complexity, penalizing the loss function, and reducing model overfitting. And it does this by adding a little more bias to hopefully reduce a lot of the model's variance. In general, we can think of regularization as a way to reduce model overfitting and variance by requiring some additional bias and requiring a search for an optimal penalty hyperparameter. And really, when it comes down to it, as far as the mathematics is concerned, regularization is all about adding in these penalty hyperparameters. Now, there's three main types of regularization we're going to be discussing here. The first is L1 regularization, which in terms of linear regression is going to look like lasso regression. Then we have L2 regularization, which is going to be discussed in ridge regression. And then we can combine L1 and L2 penalties to create elastic net regression, essentially a combination of L1 and L2. Let's discuss first L1. L1 regularization, recall that's lasso regression, adds a penalty equal to the absolute value of the magnitude of the coefficients. So what this does is it limits the size of the coefficients in the regression equation. Keep in mind that this can yield sparse models where some coefficients actually become zero. We've already seen in our discussions on polynomial regressions that coefficients can get very small. When it comes to something like L1 regularization, it will go ahead and just treat those as zero, which can help you decide which features are not even to be considered in regards to your model's output. As far as what mathematically L1 regularization looks like, it's simply going to add in this penalty term to the residual sum of squares. Don't worry too much about understanding this full equation right now. We're going to have a much deeper dive into all the equations and penalty terms for the additional minimization cost functions we produce when we're discussing regularization. The main thing to note here is that this is actually the same error we were trying to minimize, that residual sum of squares, with the addition of a penalty term. And you'll note here that the penalty term, highlighted all the way on the right, has the absolute value of the beta coefficient as something we also need to minimize, times this lambda coefficient. And that lambda coefficient is a hyperparameter that we can tune. When it comes to L2 regularization, it's also adding in a penalty term, but in this case, the penalty term will be equal to the square of the magnitude of the coefficients, which means all coefficients are actually then shrunk by the same factor, and it does not necessarily eliminate coefficients entirely. Mathematically, that error term will look like this. Notice it's again the same residual sum of squares error that we're trying to minimize with the addition of the penalty term. And in this case, the penalty term is just that coefficient squared, again, times some lambda tuning parameter. So both L1 and L2, they're just adding in a penalty term to the error we're already trying to minimize. One just happens to be the absolute value, and then L2 happens to be the squared. But both have this lambda coefficient parameter that we then have to tune and decide, which essentially just decides on how strong the penalty should be. In theory, if this lambda parameter was 0, you're no longer performing regularization. Instead, it just becomes the residual sum of squares. Again, we'll discuss these details of the mathematics behind the error we're trying to minimize when we discuss both ridge regression and lasso regression and elastic net in more detail later on. Speaking of elastic net, let's go ahead and discuss it. It essentially just combines L1 and L2 with the addition of an alpha parameter, deciding the ratio between them. If we just take a little bit of time to look at the intuition behind the mathematics of that alpha term, we can see that if alpha was equal to 0, that would mean we wouldn't consider the absolute value term, because it would just be 0 times the absolute value term, which is just 0, so you wouldn't consider it. In which case, on the square term, you have 1 minus 0, which gives you 1/2 times that beta squared coefficient, and we know trying to minimize the half of something is the same as trying to minimize the whole thing. And then we can imagine if alpha was equal to 1, that means we just have 1 times the absolute value term, so you're just considering the entire absolute value term, and then on the left-hand side for that square term, you have 1 minus 1. So then you end up getting 0 divided by 2, so you're essentially getting 0 times that coefficient squared, so now you're not considering the coefficient squared at all. So clearly we can see here alpha is just showing up the ratio of how much you're considering L1 versus how much you're considering L2, instead of trying to choose between completely L1 or L2. Keep in mind, sometimes when you're performing elastic net and you're trying to tune to the optimal alpha parameter, it sometimes will automatically tune to just alpha equals 0 being the best or alpha equal 1 being the best. So keep that in mind. Basically, your tuning just tells you only consider L1 or only consider L2. So these regularization methods do have a slight cost to them. One thing is that they do introduce that additional hyperparameter, such as alpha and the lambda terms, that needs to be tuned. And when we're talking about tuning the hyperparameter, we essentially just have to guess and check. So we're going to run the model multiple times with multiple potential values for lambda, and then using something like cross-validation, we can check what the optimal term was. And we'll discuss cross-validation in more detail later on. So we can just think about this additional hyperparameter as a multiplier to the penalty to decide the strength of the penalty term. Later on, we will actually cover L2 regularization with ridge regression first, due to the intuition behind the square term being easier to understand. The reason I mention this is because I don't want you to think we just skipped L1 regularization. We just personally think that understanding ridge regression is actually a little easier to do intuitively than trying to understand L1. So we'll first actually cover ridge regression, then lasso regression, and then elastic net. So keep in mind that we're kind of swapping that order a little bit. Now, before we dive straight into coding regularization of scikit-learn and applying it to what we already know about the regression problem with the advertising dataset, we need to discuss a few more relevant topics that are going to specifically apply to how we actually tune that hyperparameter for the penalty term. And that includes feature scaling and cross-validation. So I'll see you at the next lecture where we're going to discuss feature scaling and how it applies to a variety of machine learning models. I'll see you there.